Okay, so here's an explanation of the quiz we took. Question number 1. A boy runs and jumps horizontally off a dock 5/4 of a meter above the water. So this is, this is using, let's put a bunch of room here, using final position equals 1/2 AT squared plus V sub I t plus D sub I. This is in the vertical direction, so we know our final position is this if the dock is 0. Half of the acceleration is that, t squared, and these things are 0. So you see the negative 5's cancel out, giving us 1/4 is t squared. Take the square root. Time is half a second. And so if they go a horizontal distance of 2 meters in half a second, they have a speed of 4 meters per second and that's in the horizontal direction. Question 2, projectile explodes at the top of its arc. So picture would look something like this. It's saying the distance it normally would go is what was that? Oops. Erase. Oh gosh. Let's see. First piece, if the projectile had not exploded in flight, it would have landed 1 kilometer away. So we're assuming that that is 1 kilometer from the starting point. So this distance would have been 1 kilometer. Yet, up at the top of its path, right here, it explodes into 2 equal pieces. One of them drops straight down. So this is kind of a conservation of momentum, meaning the momentum of the entire object was enough to push it a horizontal distance of this, but because half of it is going straight down, the other half is going to go twice the distance it would have. So like this. And if you consider sort of the average, here's half the object, here's half the object, the whole object would have landed there, which is halfway. So that gives us 1.5 kilometers as the distance traveled. Each of these is half, half, half. Number 3, this is related to the monkey question. Soldier hiding in a tree fires a rifle horizontally. This doesn't really matter, but whatever. And another soldier hiding in a tree half a mile away. So when I read through this, I thought, okay, a mile is 5,280 feet, half of that is about this, and I was trying to figure out the time it took before I actually read the question, which probably wasn't that smart. The soldier in the other tree simultaneously rolls off his branch and falls to the ground. So we have a situation where there's a cliff, here's the gun, here's the tree, and here's the other soldier. I don't know, I'm going to make him just a blob. So if the bullet just went straight, it would go like this, but it's actually going to fall, and it's going to fall just like, or at the same rate as the soldier. So the bullet is either going to hit the soldier in this situation, or if this might be a really fast bullet, and so a real bullet would go like this. So there is the possibility that the bullet would hit the ground and the soldier would hit the ground over here, giving this. Okay, so it hits the soldier unless he is too close to the ground, meaning the soldier hit the ground before the soldier and the bullet could have intersected. So it depends basically on the height of the tree. question 4 is describing this. So projectiles fired upward at 90 degrees, and then a similar one is fired at 60 degrees. So meaning the same speed. And we're looking for the ratio of, we'll call this height 6 and this height 9. So the ratio of, well, how high they go. Hopefully you made a triangle where this was 60 degrees, and it looks something like this. So this is key here, root 3 over 2. You know this is 1/2, but we don't care about that. So if this is 1, this is root 3 over 2. That's the ratio of their initial vertical velocities. I think I'm going to create another page. Add to the existing recording. Okay. So this actually ended up being the correct answer. And if you want, ask, and I will show you that derivation. But that little nifty formula, the, what was it? Velocity in the y direction is equal to square root of 2gh. So that works for things falling, that works for projectiles fired up into the air, and can come in handy. So if you like memorizing stuff, that would be a good one to memorize. Alright, 5, stunt flyer in a small airplane attempting to land on the back of a truck. So, assuming the truck stays at the same speed, in order to land on the small truck and not crash, that's sort of key. So if we look at these graphs, the plane is obviously going slower than the truck. That's kind of weird, but whatever. So first of all, the plane is going to have to, let me use a different color. This is going to be good. So in blue, we have the plane. The plane. And the truck is going to go at the same speed. That was a joke, by the way. The plane. The plane is going to have to speed up and then actually decelerate or slow. Sorry, I didn't say decelerate, although the question did. Slow down so that it's going. It has to be going the same speed as the truck in order to not crash. So imagine a truck. Oh yeah, great truck. And there's this plane, some super stunt person, and it has to land right here. If it were going really fast, it would crash into here and explode. So our answer ended up being accelerate, then decelerate. Okay, last one. Bungee jumper jumps from a bridge. Height equals 0 into a deep ravine, and her position and velocity are correctly given by. So this looked correct. Alright, this was a little suspect because in general position time graphs and velocity time graphs don't look the same. But so the reason this isn't right is this little section right here. Okay, when the person, need a little space here. So when the person, here's a cliff, okay, when they first jump, their position time graph would actually, this is supposed to be a nice smooth parabola, it's supposed to look like that. Okay, so we have position and we have time, nice smooth parabola, because their initial velocity in the vertical direction is 0, so the slope of this is 0, and they speed up and speed up and speed up and speed up, meaning the slope's getting steeper and steeper and steeper. So this little graph right here would have been correct if it had done this, okay? And in addition, the bungee probably, it would probably be more like this, because the bungee is going to be sort of a sharp change in acceleration, meaning greater than, like this is showing the acceleration due to gravity, right? The acceleration of the bungee would be sort of sharper, so it would probably look more like that, sort of like a ball bouncing on the ground. And this is just totally wrong. The velocity should start at 0, that's good, and should increase in the negative direction, but acceleration due to gravity is constant, so it would be a straight line until they hit the bungee, and then it would sort of slow down abruptly, and then it would be like this, and then like this, and then like this. Okay, good stuff. So I'm going to run out of space. So this is velocity in the y direction. So this one, the one fired at an angle, has an initial velocity that is root 3 over 2 in relation to this initial velocity of 1. So what we're looking for is height and how it depends on initial velocity in the y direction. There's a sort of a fancy, I don't know, no, it's not fancy, it's actually kind of simple, but it's this, that the height is the square root of 2g, no, it is that the velocity in the y direction would be the square root of 2gh. And I'll go through the derivation later. I think I'm going to run out of time here. But what this tells us is that if we square both sides, the velocity in the y direction squared is proportional to the height. So we can find the ratio of the heights by taking the velocity in the y direction and squaring them, giving us 1 over here and 3 over 4 over here. So this is sort of a ratio of the heights that these projectiles would attain. So the ratio of this to this is 3/4 to 1, which is just 3/4.